Hi everyone, this is Mrs. GA, and today we're going to talk about one-to-one functions and their inverses. Alright, so first we're going to talk about the definition of a one-to-one function. So we know that the definition of function is that for every x, there is exactly one y. But the definition of a one-to-one function, so a more specific function, is for every y, there is only one x. So this essentially means that f of x sub 1 will never equal f of x sub 2 for any x sub 1 and x sub 2. So essentially, x's don't share y's. So for your entire function, each y value is only defined once. So hopefully you remember that we use the vertical line test to see if an equation is actually a function, but we use the horizontal line test to see if a function is considered one-to-one. So essentially, if it passes the horizontal line test, as you can see in function A, this one is one-to-one, because for every x value, there's only one y, and for every y, there's only one x. But if you look at this next one, it does not pass the horizontal line test, because you can see right here, your graph is actually crossing 3 different times. So that means that this x value has the same y value as this one, which has the same y value as this one. So we say that this is not one-to-one. And this will be important when we start talking about the inverse of a function. All right, so now let's actually talk about the definition of an inverse function. So if f is a one-to-one function, so this is where that one-to-one comes into play, then its inverse function, which we denote like this, we don't read this as f to the power of -1. This means the inverse of x, or of f, is defined by, well, if f of x equals y, then f inverse of y equals x. So what does this mean? Well, this just means that for an inverse, all x and y values are swapped. So you could literally take the coordinates from your original function, swap the x's and y's, and that would be the coordinates of your inverse function. And one reason why this is happening is because inverse functions are always a reflection over the line y equals x. And to reflect something over this line, all you do is swap the x and y values. So this is another way that you could consider finding an inverse, is by reflecting your original function over the line y equals x. All right, so let's look at this first one together and see if we can use what we know about inverses to help us evaluate our inverse. So we are given that f of 1 equals 5, f of 3 equals 7, and f of 8 equals -10. So these would be 3 coordinates for our original function. Now if I just simply swap the x and the y, those would be coordinates for my inverse function. So if I want to find f inverse of 7, that would just be 3. Remember, we swap the x and the y value. So if f of 3 is 7, f inverse of 7 is 3. That means that f inverse of 5 would be 1, and f inverse of -10 would be 8. So if you know that property of inverses, problems like these are really easy. Okay, so now we're going to talk about what's called the inverse function property. And this essentially states that if you plug an original function into its inverse, or an inverse into the original function, and you evaluate that composition, you should always result in x. So we can use this property to test if two functions are inverses of one another. All you need to do is plug the function into its inverse, or vice versa, and simplify, and if you end up with x, then they are in fact inverses. Okay, so let's give this a try. So we're going to verify algebraically that f of x and g of x are inverses using that inverse function property we just talked about. So one thing we could do is we could do f of g of x and see what it simplifies to. So let's try that first. So g of x is cube root of x, so I'm going to substitute that into f of x. So cube root of x cubed, and if you simplify that, we get that f of g of x is x. So this is enough to verify that they are inverses, but just to show you, you could also do g of f of x. You can plug f into g. So f of x is x cubed, which I will substitute into g of x, so cube root of x cubed, and again, this simplifies to x. So this verifies that f of x and g of x are, in fact, inverses. Okay, go ahead and pause the video and see if you can algebraically verify that f of x and g of x are inverses. We'll check your answer in just a moment. Okay, so here you can see that I showed both f of g of x and g of f of x. One is enough to show, but if you ever want to double check, you can try the opposite and see that they both simplify to x. Okay, the last thing we're going to talk about today is actually how to find the inverse function given one function. So it's pretty easy to do. First, you're going to switch x and y in your equation, because we know that for an inverse function, all of the x and y values are swapped. And then all you need to do is solve for y. Because, of course, this is a function, and we like to write functions as y equals blank. So then this will be your inverse function once you've isolated y. One thing to note is, just like you swap the x and y values, the domain and range are also swapped for your inverse function. So if you know the domain and range for your original function, you swap them for the inverse. Okay, let's try one more example together. So here they're asking us to find the inverse of f of x equals square root of x minus 2. So before I do anything else, I know that square root functions have a restricted domain and range. So let's find that of our original function first. So for our domain, we know that you can't take the square root of a negative. So our radicand, which is x minus 2, must be greater than or equal to 0. So x must be greater than or equal to 2. So our domain here is 2 with a bracket to infinity. For our range, this might help to sketch a picture of this graph. So if you look at what this square root function looks like, we know that the parent function of square root looks something like this. This graph is shifted to the right too, so you get something like this. So you can see that our range is going to be everything 0 and above. So our range is 0 to infinity. So it helps to define the domain and range of your original function before you find the inverse. So when you have your inverse, you just swap them. So now let's actually find the inverse. So remember, the first step is to actually swap x and y in your equation. So I'm going to write it like this. X equals the square root of y minus 2. And now all I need to do is solve for y. So I'm going to start by squaring both sides. So we have x squared equals y minus 2. And then I'm going to add 2 to both sides. So y equals x squared plus 2. This is our inverse, so I'm going to take one more step and actually write it with the proper notation. Now it's also important to note what the domain and range of our inverse is. So our domain is going to be 0 to infinity, which was the range from our original problem, and our range is going to be 2 to infinity, which was the domain from our original problem. And this is really important because while this is a parabola, with this restricted domain and range, we would actually only use part of this function. Okay, why don't you pause the video and give this last example a try. See if you can find the inverse of f of x equals 3x minus 2. All right, let's check your work here. So again, swap x and y, solve for y, so make sure you add 2 first and then divide the entire thing by 3, and then write it with the proper notation. For this one, the domain and range of f of x are all real numbers, so the domain and range of our inverse function are also going to be all real numbers, so negative infinity to positive infinity. All right, that is all for today's lesson. Thank you for watching.